I'd like to thank the organizer for giving me the opportunity to present this work today. And I would like to start by taking you to the central Andes in the Eocene pluton called the Andahuayla theory batholith. This is a largely underdeveloped district, mining district. All these dots here, they are actually porphyry copper and skarn copper deposits. And at the moment, there are two active districts in the area, the Tintayaco one, which hosts at least more than 13 million tons of copper. And there is the Las Bambas Haquira district hosting more than 20 million tons of copper. This is only what is known at the present time. And so it's largely underdeveloped. And let's assume today that we are in a board meeting for a mining company, all of us involved. And we have money to invest in projects. The thing is that we only have money to invest in one of the projects. And after careful selection, we've came out that these two might be the best candidates. The thing that they are actually incredibly similar. Every characteristic is similar. And if we look at, for example, the available resource report, the Alpa deposit hosts something like 3.9 million tons of contained copper. There has been a few years of exploration there. And this is what has been defined so far. The Kucha deposit seems a little bit bigger, although it has a smaller grade of 0.5 million tons of contained copper. The strontium and yttrium values of the porphyries, as Massimo suggested, this is in the good range we would expect from a good porphyry. Yet, at both of these deposits, the mining companies, the exploration companies, got the very good idea to do high precision geochronology. And this is the result. So they found in both cases pre-mineralization plutonic rocks dating, being significantly older than the porphyries. They've dated few porphyries available on the site, postal porphyry and also some molybdenite. And based on this data, I'm sure you've guessed, and after Massimo's talk as well, that I would advise that we should invest in the Alpa deposit. By the way, these deposits are fakes. This is just for the sake of the demonstration. Don't even try to look at this on the internet. So, yeah, in this talk, I will show you why I believe we should invest in the Alpa project and why I believe actually this tonnage here can be increased by up to an order of magnitude, probably. So when we talk about magmatism associated with porphyry copper, there is two very contrasted models, ideas, and of course the truth is always a little bit in between. There is the idea that we might need fertile magmas. This might be suggested by some chemical indicators of the whole rock, like the strontium yttrium values, the serum anomaly in the zircon. It's hypothesized that this magma are more oxidized, more hydrous, sulfur-rich, copper-rich, maybe chlorine-rich, compared to, let's say, normal arc suites. But how significant is this for the formation of porphyry deposits is a question. On the other side, there are some fluid inclusion work showing that barren and mineralized systems actually have similar metal concentrations, and they seem to be equally good from a fluid perspective. And early modeling carried on at the Yerington Pluton batholith suggested that the magma was fairly normal copper concentration. I think it was something like 50 ppm at that time. Can form JNPCD, can explain the Yerington deposits. But of course, something very important in both of these cases is that we have an efficient sulfide precipitation and a good preservation plus minus some supergene enrichment. And I will not address this question today. I will mostly focus on the magmatic side of the story. The problem is that when we want to study porphyry copper deposits, we want to look at the magmatic side. Most of it is buried quite deep below the deposit, and we have no access to this. Our only window is a few square kilometers of very altered rock, and it's not a very good situation. On the other side, where we have a beautiful pluton outcropping on surface, we have no idea if there has been any porphyry on top. So one way to look at this is to do some modeling, and today I will specifically focus on this underlying pluton below the porphyry systems. And again, I will not address this part of the precipitation. So what we know about plutons in the crust is that they are not emplaced instantaneously. They are emplaced incrementally. This is a nice example from the northern Italy, from the Alps. This is the Adamello batholith. And the geochron data show that this batholith has been emplaced over about 10 million years in this area. And this is the sort of important constraint we need to implement in any model of degassing that we would like to carry. And in this model of degassing, we will specifically focus on the composition of the fluid to see at least if the fluid we compute is similar to the fluid we can measure in fluid inclusions. And we will also focus on the dynamics of outgassing, which is the flux and the timescale. And this will branch with Massimo's talk. So what I will try to show you later in this presentation is that a fairly normal hydrous magma can outgas fluids very similar to ore-forming fluids, the one we measure, that no enrichment is required. It does mean it's absolutely welcome, but it's not absolutely required. This is an important distinction. And the copper endowment on first order would be controlled by the volume of magma, as Massimo showed as well. But of course, some enrichment will help improving this endowment. And I will insist that high-precision geochronology may be used to provide some rough estimate of the maximum possible copper endowment in a given system. So this is a thermal model for an incrementally building pluton. So the magma is injected in the center here at a given flux, which is here 10 to the minus 2 cubic kilometer per year. And this is the thermal field after 50,000 years. We want to have a look at how this pluton is outgassing through time and through growth. And let's focus at one very tiny fraction, a small cube of this magmatic system, which is here. So as it cools, it would, let's assume it's water saturated. So as it cools, it would crystallize some crystals, and it will start exsolving bubbles. And we will assume for now that the bubbles don't escape instantaneously. And this is backed up by some physical models of magma outgassing. And that bubbles will only escape when they reach a threshold of percolation, which is when they reach a certain volume within the magma system. And there they escape. Then the magma keeps crystallizing. There is a second outgassing event, a second percolation threshold, and this fluid escapes. And what we then, so on and so forth. And what we see here is that during cooling, magma outgassing happens at sort of fixed temperature. So if we track this isotherm corresponding to these 4 cycles of magma outgassing for a given very small volume of magma, we can sort of assume that outgassing occurs along these 4 fronts of outgassing, and the fluids that is coming from the system, the total fluid, is actually a weighted mean of the 4 fluids that are outgassed along the 4 outgassing fronts. So if we want to compute the composition of the fluid, of course we need starting parameters. The aim of the study was not designed to correspond to a specific system, but more to embrace the variability in nature. So we chose a Monte Carlo approach with a range of initial composition, a range of KDs. We assume that the magma is emplaced at about 10 kilometers with 5% dissolved water. And we also vary the final volume of the magmatic system from 100 to 10,000 cubic kilometer. We emplace different magmatic flux to see the influence of the fluxes. And we inject the magma at different temperature. And this is the result of the fluid composition through time, focusing on copper, sulfur, salinity, lead, and zinc. And what we see, first of all, which is quite striking, is that in all of these plots, during degassing, so even after the end of magma injection, the composition of the fluids, of the intermediate density fluid, high temperature, coming from the magmatic system, stays relatively stable. Second, so these bin plots here, this is the bin plot corresponding to the value we measure in intermediate density fluid inclusions at porphyry systems. What we can see is that for salinity, there is a perfect match, an equally good match for zinc, really good match for lead as well. As for sulfur, this red stuff here corresponds to the typical limit of detection on the analysis we can carry on today. So I would say that there is a fairly good match, and especially we reproduce the highest density of points here. And the same for copper, which is known to be extremely easy to diffuse in this fluid inclusion. But yet, we reproduce the highest density of points for the copper concentration. So I would argue that this shows that at least computationally, we can reproduce the fluid that is measured in such porphyry systems. Now, another aspect is to vary the flux, the magmatic flux in the system. So here is a plot of the copper flux depending on the flux of magma injection, so we chose 3 different fluxes. This dotted line here is the cumulative amount of extracted copper. And what this plot shows is that at low magmatic fluxes, all of the copper is outgassed during magmatic injection. But if we keep increasing the magma fluxes, a significant portion of the copper is outgassed after magma injection has ceased. And in this case, it's about 20% of the total copper that is outgassed after the end of magma injection. And in this case, it is 30% of the copper that is outgassed after. So maybe we can use also these timescales to have an idea about how much copper we can outgas, and what was the average flux of the magma injection in the system. So as I told you, we choose different fluxes. We choose different, we computed the model for different volumes of magmatic system. And for each of these points, we have the duration of magma injection and the duration of fluid release. And we can simply contour this plot for these 2 durations. And I will explain you how to read this with this example in the blue field here. So in the blue field, this would correspond to a magmatic system that has been infilling for about 500,000 years, so 500,000 years. And the magmatic, the fluid release actually took 750 years, 50 kilo years on average, and this would correspond to a magmatic volume in the volume of magma in between 1,000 and 2,000 cubic kilometer, and an average flux of 2 to the minus 3 cubic kilometer per year. This is a way to read it. But now, if we know the volume, we can play a mass balance calculation and have an idea of the maximum mass of extractable copper from this system. And so this magmatic system would correspond to a fairly big range. But of course, if we got more precise value for the KD, for the initial copper concentration in the melt, we can narrow down this probability density curve. And so now we can have a look at natural system, known porphyries. And this would be an example, 3 examples, one from El Teniente, Culong, Abajo de la Lumbrera. And we've estimated the timescale of all related magmatism, and together with the timescale of mineralization based on the uranium and molybdenite. And if we plot these results on the framework I showed you before, this is what it ends up. That El Teniente sits on the top, Culong in the middle, and Bajo de la Lumbrera sits on the bottom. And this correlates very well with a measured copper endowment in the system that we know from studies, from exploration and mining. And what's interesting here is that this curve here is the probability density curve of the world average pluton filling rate. And it shows that a porphyry copper system corresponds to a magmatic flux that is similar to normal plutons. This is also, I think, an important constraint that we should consider. And so this diagram suggests that the timescale can be used as a very rough estimate of the measured copper endowment, of the maximum possible copper endowment. And if we add more deposits dated with a much lower precision, and this is probably why we got these big fields and not this very tiny one, we still have this systematics, assuming now we got a normal flux. we still have this systematic that the largest deposit sits way on the top on the side of the high volume system, and the small deposits like Corocohuayco, Bajo de la Lumbrera sit on the around 100 cubic kilometers. So I hope you're convinced that we should invest in ALPA, and there is potential for much more copper in this deposit. So I would say that the largest deposit needs a lot of magma, really a lot. Potentially normal. Enrichment is welcome, of course, so I still keep a tiny bit of hope that we can improve the copper endowment with this. As Massimo showed, strontium is a proxy for the accumulation of large quantities of magma, but the duration of PCD formation points to the volume of magma that has actually been transferred to the upper crust. Thank you very much.
We've got time for a couple of questions. Wait for my glamorous assistant in his microphone. I think Paul.
I noticed that you use 2.5 kilobars, or 250 megapascal, as your pressure of fluid extraction or equilibration with the metal. Is that a weighted average of the pressures at which the fluid's exhaust?
Yes.
So some of it's 5 kilobar or 500 megapascals, some of it's 100 megapascals and so forth.
Exactly.
Okay, and the basis of these KDs is?
Well, no, not yet, because at the time I was doing this this work, it was not yet ready. Now I should definitely incorporate this. Now, the KDs is a range of published values that we found. And of course, it's always tricky to say, I decided to select this value because it fits better with my model. So I just chose all of them and took the smallest, took the biggest, and model everything in between. But it fits, by the way, with the KDs that Brian and John are releasing for chlorine, for example, and for copper. It fits very well.
We'll have time for one last question, if anybody's got. Jamie?
Yeah, I was wondering about the values that you used for fluid inclusion chemistry to compare with your model results, because you're kind of, I guess, using the median in a sense to compare across. And I'm wondering how much you've actually already lost some of the metal from a lot of the fluid inclusion data. Typically, when we see fluid inclusion results from porphyry systems, there's a huge range. And it may be that the actual kind of primary fluids are much nearer the top of that range, and the rest that we're measuring is a lot of fluids that have already precipitated some stuff. So I was wondering if you could just comment on that a bit more. The copper values we often see are more around the 1 weight percent rather than down at sort of 0.1, at the top end of the range. Well,
as you've seen from the probability density, it seems most of the copper value, the highest density comes to the lower than a percent. But as you say, this is something I didn't consider. Yet, this compilation is the compilation from Kalin Kuzmanov for the fluid inclusions. And we only took the intermediate density, high temperature fluid inclusions in this compilation. So there is a potential that some of these indeed reflect a lowering copper content during precipitation. But I'm not sure how big would be this difference.